So next we're going to look at transient analysis in PSpice. As I introduce transient analysis in the beginning of uh, the video lecture series, that transient analysis is analysis with respect to time. So if your voltage, current, power values are changing with respect to time, then you use transient analysis. Now, transient analysis can be done with DC sources or AC sources. Uh, but if you have only resistors in the circuit and DC source, then in general, the values of voltage, current, they do not change um, through resistor. They will always be constant. So you don't really perform transient analysis if you have only resistors in the circuit with a DC source. But if you have inductor, capacitors, those are energy storage components, and they take time to charge, and then they can also discharge. So you can see the charging and discharging effect even if you have the DC source, and if you are bringing any change in the circuit. That is, if you have a switch that you're turning on and off, so you are changing the energy stored in these components. So you can see that current and voltages are changing. But all these you're going to discuss in circuit analysis course. Here we're just going to concentrate on the simulation. So if you look here, transient analysis, and one example is given over here, in which I have a simple circuit. I have an inductor, I have a resistor, and I have a switch. Now observe this switch. There are two switches in PSpice, and let me go ahead and show you where they are. So I created this circuit, which is similar to the one I showed you. The only difference is I put two resistors instead of one resistor. So these switches, they are in the eval library, which are S switch T close and switch T open. So there are two switches here. And the whole purpose of these switches are that they provide connection at a specific time if it is T close. So this is going to close at 4 millisecond. And I chose 4 millisecond. If you just put the switch, for example, if I go ahead and put the switch, you will see that it says 0. So if you want to change the value to any value that you want, like I did, 4 millisecond, then you can go ahead and click on that and you can change the value. And likewise, you have switch open. Switch open basically is going to open the switch instead of closing it. But the effect is same, that it's going to open up at a specific time, so it's going to disconnect that part of the circuit where the switch is connected. In any case, so if you want to apply transient analysis on this circuit, I'm going to go ahead and show you the simulation setting window. So of course, you're going to go ahead and you're going to create a new simulation profile. I just created a profile, and out of the 4 simulation type, you have to choose the transient, time domain transient. The first one, run to time, is the total time for which you want to run the simulation. So I'm running it for 10 milliseconds. Start saving data means what time it's going to show you this, what time it will start the simulation for you. So I'm doing it at 0. That means I want to go from 0 to 10 milliseconds. If you want, you can go at 2 milliseconds, 3 milliseconds. So it's going to start from that time and it's going to go up to 10 milliseconds. In general, if some of the advanced circuits, if you are going to take power electronics class, then some of the circuit, they take a very long time before they get to the steady state value. That is the state at which they are moving between the two constant values. That's called a steady state value. So we run the simulation for long amount of time, but then we only want to see the last few millisecond or microsecond of the simulation where it gets to the steady state. We are not interested in the whole simulation. So in those cases, you put the time, let's say 9 milliseconds. So it's only going to run, it's only going to show from 9 millisecond to 10 millisecond. Maximum step size is how many points you want to plot. In general, the more points you're going to plot, the smoother the curve it is going to be for your simulation. The less points you're going to plot, the coarser the curve is going to be, or you will have sharp edges in your simulation. So anytime you have sharp edges in your simulation or your waveform looks very coarse, go ahead and reduce the size of your step size. So I'm keeping it about 0.01 millisecond because I'm running from 0 to 10 millisecond. So in 1 millisecond, I'm going to have about 100 points, right? 1 millisecond over 0.01, 100 points. So 10 millisecond, I will have about 1000 points. So I'm plotting about 1000 points from 0 to 10 millisecond. And that's it. You apply, you OK. And I'm going to go ahead and run the simulation. All right, everything worked out, everything checked. And let's go ahead and put the current probe to see how the current is changing in the circuit. So if I want to see how the current is changing through inductor, observe that as long as the switch is not closed, of course, there is no current flowing in the circuit, because when the switch is open, of course, there is no path for the current to flow, right? Your switch is off. When you close the switch, you turn the switch on, then the inductor starts charging, and it shows the charging pattern. So it's like exponential pattern for the charging, as you're going to study in circuit analysis next semester. So you start charging, and then it becomes a steady state. Actually, some of you are taking circuit analysis this semester, circuits 1, but this is specific phenomena of charging and discharging, what we call transient analysis, is discussed in circuit analysis 2. So this is how the current is changing with respect to time, right? You can do the same thing with the voltage as well. Let's say you want to see how the voltage is changing across R2. So you put voltage probe, and this is how the voltage is changing across R2. You want to see how voltage is changing across the inductor. Now remember, since none of the end of the inductor is grounded, you cannot choose a single-ended voltage probe. You have to choose the double-ended voltage probe. So you're going to put one here, you're going to put one there, and you're going to see that it was 0, and then at 4 the voltage in inductor jumped to 10 volt. That is all the voltage of the source voltage appeared across inductor, and that's one of the characteristic of inductor. As again, you're going to discuss that theoretically. I'm not discussing it right now. And then it starts going down, because eventually inductor is going to become short circuit when it is fully charged. When the source is DC, at the steady state, it acts as a short circuit, hence the voltage across it becomes 0, and the maximum current flows through inductor. So this is what the transient analysis is. So remember, few important things that you need to remember when you're doing transient analysis. Again, run to time is the maximum time for which you want to run the circuit. Start saving data means at what time you start your simulation. So at what time you're going to show the simulation over here. So let's say if I go and change this to 2 millisecond. Apply. So now observe, my simulation is starting at 2 millisecond, not 0. Okay. And again, most important thing is the step size, because many students they're not very careful about the step size. And when I see their simulation, they have like sharp edges in their simulation because they're plotting very few points, or their simulation is very coarse. So make sure it's important that you understand what the maximum step size is. Okay, now one important thing, how to read the values from the graph. So let's say if I ask you, hey, read the value of the voltage at 4.5 millisecond. Now you can go and you can kind of estimate that the value of the voltage across inductor at 4.5 millisecond is somewhere between, let's say, 3 to 4 volts or 3.5, so somewhere between 3.5 to 4 volt, right? Here's the value. But how are you going to exactly read it? And to exactly read it, you use cursors. And to activate cursors, you press this toggle cursor button. Now there are two cursors. One cursor, and I'm going to go ahead and I'm going to close this window right here, and I'm going to close this window and this window as well. So I'm just going to keep the cursor window open right now. Okay, so this is the cursor window where you can read the cursor values. And there are two cursors. One moves with your left mouse button, which is red, you can see right now, and one moves with your right mouse button, which is green, you can see. And since the simulation is green and cursor is green, you can change the cursor again click on it, and if you go ahead and go to tools, options, and cursor settings, you can change the value of the cursor, the color of the cursor. It shows blue, but I don't know why it's just showing. So let's say if I have one is yellow and one is kind of this color. So now one of my cursor is yellow and one is my light blue color or teal color. Okay, so you can change the color of the cursor. So let's say I told you, I ask you, what is the value of cursor at 4.5 milliseconds? So you can choose any of the cursor and you can move it to 4.5 millisecond. Observe the vertical line. Now it is at 4.5 millisecond, right? So if you go to the yellow cursor, which is the first one right here, y1 and y2 is the blue, at 4.5 millisecond, which is the x-axis of the cursor, the value is 3.624 volt, right? So the value of your signal is 3.624 volt. And let's say I ask you, what is the value at 5.5 millisecond? So I can either move the yellow cursor with the left mouse button, or I can move the blue cursor with my right mouse button. And I put it at 5.5. So my blue is at 5.5, as you can see in the cursor window, and the voltage is 492.161 millivolt, right? Okay, one other important thing is the difference between the cursor values. And this will be discussed in more detail when you will do the, when you will create the amplifier circuits, your BJT amplifier and MOSFET amplifiers. Because in amplifier circuit, you will be reading you will be trying to find out the gain of the amplifier. And to find gain of the amplifier, you have to find the peak-to-peak value of the input and output voltages. So when you are trying to find the peak-to-peak voltage, what do? Is you put one cursor at the maximum peak of the waveform, and the other cursor is at the minimum peak of the waveform. And then you read the difference between the two, that is the peak-to-peak value. And that difference is right here, y1 minus y2. So the difference between the two values, that is the value of cursor y1 and value of cursor y2, that is the difference between 3.624 and 492.161 milli is 3.1502. So if I ask you, what is the difference between the values at 4.5 millisecond and 5.5 millisecond? Then of course you're going to put one cursor at 4.5 millisecond, the other cursor at 5.5 millisecond, and you're going to read the difference between the two values, which is y1 minus y2, and which is 3.1502. So this is how you toggle the cursor. There are some preset cursor values as well. So you can find the cursor peak, the peak of the waveform. You can find the bottom peak of the waveform. You can find the cursor minimum, maximum, and all those things. But you can always move the cursor, and any time value that you want to go to, you can go to the time value and you can determine what is the corresponding voltage, current, power value at that time. Once again, one cursor moves with left mouse button and the other cursor moves with the right mouse button. Okay. So if I go back and I show you, this is basically the circuit with your DC source. Now if I go back and I change this to a sinusoidal source, so I'm going to go ahead and change it to V sine. Okay, and I'm going to go ahead and remove the switch, and let's say I connect this, and I'm going to go ahead and plug in a capacitor over here. So rotate and capacitor. Okay, and let's say the capacitor value is 1 microfarad. Okay, And let's say this is 1 kilo ohm and this is 500 ohm. Now this is a sinusoidal source, that is, it gives you a sinusoidal waveform, basically the same voltage source that you have in your household that comes out of the socket. Offset is basically if your waveform is on x-axis, if your sine waveform is on x-axis, that's called zero offset, so it is riding on the x-axis. If you want to change the height of the waveform, that is such that it is riding, let's say, at 1 volt or 2 volt, that's called the offset of the waveform. So if it is riding at 1 volt, you're going to set the offset to 1 volt. If the offset is 0, which I'm going to set right now, that means it is riding on the x-axis, that is at 0 voltage, 0 DC voltage. So this determines the DC voltage at which the sinusoidal waveform will be riding on. If it is negative, it's going to be riding on the negative DC voltage. Amplitude is the peak value of the waveform. So let's say I choose the peak value of the waveform to 5 volt. Frequency is how many cycles the sinusoidal waveform has in 1 second. That's the frequency. So let's say the frequency I choose 1000 hertz, so 1 kilohertz. And don't worry about AC, leave the AC right now. AC is used for the AC sweep function, which we are going to discuss in the next video, AC sweep function. So I'm going to go ahead and show you in this case how do you set the values over here. So generally you go with the frequency. Look at the frequency of the sinusoidal wave, it's 1 kilohertz. That is the time period of this sinusoidal voltage is 1 millisecond, because time period is 1 over frequency, right? It's the reciprocal of the frequency. So the time period is 1 millisecond. That means it will have a complete waveform, one complete waveform in 1 millisecond. So if I run it for 10 milliseconds, that means I'm plotting 10 cycles of the waveform. You don't have to plot that many. Let's say I want to plot 3 cycles. So I will run it at 3 milliseconds. I'm going to start saving data after 0. And in general, whatever the time period of the waveform is, choose 1/100th of that to be your step size. So since the time period is 1 millisecond, 1/100th of that will be 0.01 millisecond, which is okay. I don't have to change that. So if you plot 100 points per cycle, your plot is going to be very smooth. So I'm going to go ahead and apply and OK. And let's go ahead and run the simulation. And let's go ahead and put any probe anywhere. Let's say I want to see what is the voltage change in R1. So I'm going to go ahead and, oops, I'm going to go ahead and put a probe here. And it's going to show you that this is how the voltage in R1 is changing, right? Once again, if you want to toggle the cursor and you want to check the values, you can always check the value. And remember, I was telling you peak to peak value. So if you put one cursor at the maximum peak, and you can also do that using the cursor peak, it's going to the first. Generally, observe that the first is smaller than the next 2 peaks. Generally, it takes a little time if you have inductor and capacitor. It takes time for inductor capacitor to charge. And then the waveform becomes, steady state, that it starts moving between the 2 constant values. So generally, we ignore the first peak if you are measuring the steady state value and go to the second, third peak. So I put it on the second peak, and I put the blue cursor on the bottom of the second cycle. So now I can measure the peak to peak value between the both, which is right over here. Y1 minus Y2. That's my peak to peak value, 9.34 volt between the two, right? Y1 is at 4.6, it's at 1.2275 millisecond, which is 4.657, and Y2 is at 1.735, which is negative 4.6821. So approximately I have 9.35 volt between the 2 peaks. This is my peak to peak voltage. This is my positive peak voltage approximately. This is my negative peak voltage approximately. This is how you're going to use cursor to find the peak-to-peak value. And this is how you can do the simulation with your AC source. So if I want to see how much power is dissipated, you go to the same thing, and it's going to show you that this is how the power is being dissipated in that R2. Okay. All right, let me go ahead quickly and let's see. So you will be doing this exercise, and in this exercise you are using the switch, but this is not the T close switch, this is T open switch. So remember, use the T open switch. It is going to open at 6 millisecond, and then you are running the simulation for 20 millisecond, and a step size is 0.01 millisecond. And make sure start saving data at 0 millisecond. At 0, start from the very start. Okay, don't start at 6 millisecond. Start saving data. Make sure it starts saving data at 0. So you're going to go from 0 to 20 millisecond with a step size of 0.01, and then you are going to see what you are measuring in here. Let's see. Find the transient voltage across R3. So R3, which is right here. As I show you, you're going to put one probe here, one probe there, and you're going to measure the voltage. Okay, transient analysis with AC sources. All right, as I discussed with you, the AC sources, cursors I discussed with you, cursors. So exercise 5, you have a circuit and you have an AC source, and I'm asking you to carry out the simulation, 10 millisecond with a step size of 0.01 millisecond, and then you have to plot 3 waveforms, input voltage VL1, VL2, and then you have to measure the voltages at these times, right? So what basically you can do is when you put your circuit and simulation in Microsoft Word file, just create a table in Microsoft Word file, and for these 3 voltages, what I'm asking you, input voltage, voltage across L1, and voltage across L2, these 3 voltages. So create a table, and then from your observation with the cursor, observe the values. What is the value of 2.3 for all 3 voltages, and then put it in that table. And then use the cursor, 5.2 millisecond, put it in that table, and then 9.0 millisecond, put it in the table. So since you have 2 cursors, you can you can measure 2 values at the same time, 2.3, 5.2, observe those values, put it in the table, and then once you have observed those values, then move one of the cursors at 9.0 millisecond, and then observe all 3 voltages, and then put it in a table in Microsoft Word file. Exercise 6 is similar. And then you have the transient analysis with non-sinusoidal waveform. So go over the pulse signal. I'm explaining you this signal basically can be used to create a voltage, square voltage, triangular voltage. In this case, I'm asking you to do a square voltage, and I'm explaining what different things are. V1 is the high value, low value of the voltage. V2 is the high value of the voltage. TD is the time delay before the first transition, before it goes from low to high, how much time should be delayed. TR is the rise time, that is the time it will take from going from low value to high value. TF is the fall time, how long it's going to take to go from high level to low level. Pulse width is the time over which the waveform is high. So if it's a square wave, and if you want the waveform to be high, if it's a square wave, then half of the time it will be high, half of the time it will be low. So whatever the period of the square wave is, pulse width will be half of that. If you want it to be more than half, that is you don't want to be exact square wave, then you can set that whatever period is. Let's say you want 60% of that. So if the period is 1 millisecond, you want it to be high 0.6 millisecond, that is duty cycle is 60%, then you can put down 0.6 millisecond, it should be high out of the total period of 1 millisecond. But for a square wave, it is half high, half low. So whatever the period of the waveform is, half of the time it will be high. So exercise 7 is basically you're going to use this voltage source, and you are going to create a circuit with resistor, inductor, and capacitor, and you're going to put all of them in series. Series means all the components are connecting back to back and making a closed loop, right? So your voltage source, resistor, inductor, capacitor, all are connected back to back and making one single closed loop. and just follow the direction and do the simulation and see how it's going to look like. Now, sometime, as I'm telling you, rise time and fall time, keep them to be 0. Sometime, um, and I don't know why, but if you keep them to be 0, you still see that the voltage is taking some time to go from 0 to the low voltage to the high voltage. It's not exactly 0. So you will see instead of going instantaneously, you see a slope basically, which does not have an infinite value. If you see that it is taking some time to go from low level to high level, make sure don't keep rise time and fall time to be 0. Choose a very small value for that, like 1 picosecond for both rise time and fall time, and that's going to fix that problem. This should be instantaneous from 0 to 1. It should not have any, if you set it to 0, theoretically it should be instantaneous. But if it is not instantaneous, just keep 1 picosecond for both rise time and fall time, and it will make it instantaneous. Okay, so this finishes up the discussion for